dear learners, for this course on finite element analysis. In our module 5, we were discussing about dynamic analysis and axis symmetry problems. So far, we have solved problems on dynamic analysis of one dimension bars. Let us discuss and conclude our discussion on dynamic analysis in today's class. Let us solve the final problem on dynamic analysis, which deals with the transverse vibration of beam. Problem number 4 of our discussion states that a beam fixed at both ends, as shown in the figure, has mass density rho, modulus of elasticity E, cross section area A, area moment of inertia I, and length 2L. Considering two elements for modeling, determine the fundamental natural frequency of vibration. Case A using consistent mass matrix, case B using lumped mass matrix, and case C also calculate the percentage error using the exact solution for the fundamental natural frequency from simple beam theory, which is given by omega n is equal to 5.59 by L square root of EI by rho A. So this is the beam which is fixed at both ends, having the cross section area A, length is equal to 2L, and area moment of inertia is I, and mass density is rho, modulus of elasticity is E. So for this bar, modeling it into two elements, I should calculate the fundamental natural frequency. In case A, I should use consistent mass matrix for calculation. In case B, I should use lumped mass matrix for calculation. And in case C, finally I should find out the percentage error from both case A and case B using the exact solution for the fundamental natural frequency of vibration for the fixed beam as shown in the figure. Let us solve this problem. Coming for step 1, that is finite element model. In the question itself, he has specified that consider two elements for modeling. So therefore, considering two elements for modeling, at node number 1 we have fixed boundary condition. Let us take node number 2 at length is equal to L, and node number 3 at length is equal to 2L, which is also fixed. So this is node number 1, node number 2, and node number 3. Regarding the boundary condition, we have already discussed in our module 3. If a node is completely fixed, then both the vertical deflection and slope at that node are equal to 0. Whereas at node 2, which is completely free, I should calculate both V2 and theta 2, which are not equal to 0. Since node 3 is completely fixed, so therefore deflection is equal to 0 and also slope is equal to 0. So the only parameters which are not equal to 0 are deflection and slope at node 2, which is completely free. We have modeled by taking lengths as length of element 1 is also L and length of element 2 is also L. This is element 1 and this is element number 2. This completes the finite element model for the given problem. Now moving on for step 2, that is element stiffness matrix. We already know that the element stiffness matrix for analysis of beams is given by EI by LQ, 12 6L minus 12 6L. Diagonally we have 4L square, 12 and 4L square. Here we will be getting minus 6L and 2L square. Since the stiffness matrix of beam element is banded and symmetric, completing the element stiffness matrix using the property of symmetry, I will get the element stiffness matrix as this completes the general expression for element stiffness matrix for beam elements. Now substituting the values of E, I and L, I can find the element stiffness matrix of element 1 and element 2. For element 1 and element 2, if you clearly observe, the modulus of elasticity, area moment of inertia and length remains same. Therefore, the element stiffness matrix of element 1 is equal to Young's modulus is E area moment of inertia is I and length is of element 1 is L. So therefore this itself is the element stiffness matrix for element 1 and also for element 2. Since we should calculate the global stiffness matrix, which is bit difficult compared to the obtaining the global stiffness matrix of bars, let us write down the element stiffness matrix and mark the nodal variables of element 1 and also element 2, using which I can easily extract the global stiffness matrix which is required. So therefore element stiffness matrix of element 1 is also equal to EI by L cube 12 6L minus 12 plus 6L. Going for the nodal variables of element 1, the nodal variables for element 1 are V1 theta 1, V2 theta 2. So marking which I will get V1 theta 1, V2 theta 2. Here I will get V1 theta 1, V2 theta 2. So similarly for element 2, if I write, I will get the same expression, but the nodal variables are different. That is, K of element 2 is also equal to EI by L cube. The nodal variables for element 2 are V2 theta 2 and V3 theta 3. So if I mark that, I will get V2 theta 2, V3 theta 3, V2 theta 2, V3 theta 3. Now finally, moving on for step 3 to find the global stiffness matrix. The order of the global stiffness matrix for analysis of beams is 2n cross 2n, where n is number of nodes. Since this problem has 3 nodes, the order of the global stiffness matrix is 6 cross 6, where these 6 are nothing but the nodal variables. That is V1 theta 1, V2 theta 2 and V3 theta 3. So let us outline the global stiffness matrix, and using the order of 4 elements at a time, I can construct the global stiffness matrix. That is step number 3, global stiffness matrix. Now initially marking the nodal variables, we have EI by L cube common. The nodal variables are V1 theta 1, V2 theta 2, V3 theta 2. Here we have V1 theta 1, V2 theta 2 and V3 theta 3. Coming for the element number 1, so all the matrix will fit into in the order V1 theta 1, V2 theta 2 cross V1 theta 1, V2 theta 2. So therefore, filling it up as it is, we have V1 theta 1, V2 theta 2 cross V1 theta 1, V2 theta 2. So placing it in the respective positions, I will get 12 6L. Now coming for the element stiffness matrix of element 2, it will fit into the global stiffness matrix in the order V2 theta 2, V3 theta 3 cross V2 theta 2, V3 theta 3. And to avoid confusion, let us take 4 at a time. If I take these 4 elements, the order of these 4 elements is V2 theta 2 cross V2 theta 2. So if I pick this, it will overlap on these 4 elements, that is V2 theta 2 cross V2 theta 2. So 12 plus 12 will become 24 plus 6L minus 6L will become 0. 6L minus 6L will again become 0. 4L square plus 4L square will become 8L square. Now coming for these 4, we have order V3 theta 3 cross V2 theta 2. That is V3 theta 3 cross V2 theta 2. So filling which I will get minus 12 6L minus 6L 2L square. So coming for these 2 rows, it begins from V2 and ends at theta 3 in the row V3. So in the row V3, I should start from V2 and end at theta 3. So if you do that directly, I can write it as minus 12 minus 6L, 12 minus 6L, and the last one is 6L, 2L square minus 6L, 4L square. Now fill the unfilled positions with zeros. So here we will get 4 zeros, and at the bottom left corner also we will get 4 zeros. So this completes the global stiffness matrix for the given problem. Now moving for step 4 to find the element mass matrix. Now we already know that the element stiffness matrix and also the global stiffness matrix remains same for both case A and case B calculations. That is, calculating the natural frequency using consistent mass matrix in case A, and in case B calculating the fundamental natural frequency using lumped mass matrix. For both the cases the global stiffness matrix remains same. So therefore step 3 is same for both case A and also for case B. Coming for step 4 onwards, the problem deviates. So let us take up case A. Let us find the natural frequency using consistent mass matrix. Coming for step 4, the element mass matrix. The element mass matrix for beam element is given by the element mass matrix. General expression is mass matrix of any element is equal to rho A L by 420, 156, 22L, 54 minus 30L, 4L square, 13L minus 3L square. Again we will have 156 minus 22L, 4L square. This mass matrix is also symmetric. So therefore, using the property of symmetry, the element mass matrix will become N. Now, if you observe the density, area and length for both element 1 and for element 2 are same, which are nothing but rho A and L. So therefore, this itself is the element mass matrix for element 1 and also for element 2. To construct the global mass matrix, let us write the element mass matrix for element 1 and element 2 individually and mark the nodal variables of element 1 and element 2. If I do that for element 1, we will be getting element mass matrix of element 1 as rho A L by 420, 156, 22L, 54L square. Whereas the nodal variables for element 1 are V1 theta 1, V2 theta 2, V1 theta 1, V2 theta 2. Similarly, for element 2, if I write, I will get the element mass matrix of element 2 as the nodal variables for element 2 are V2 theta 2, V3 theta 2, V2 theta 2 and V3 theta 2. We already know that the order of the global mass matrix for analysis of beams is 2n cross 2n, where n is number of nodes. Since this problem has 3 nodes, the order of the global mass matrix is 6 cross 6. These 6 are nothing but the nodal variables. They are V1 theta 1, V2 theta 2 and V3 theta 3. That is, moving for step 5, global mass matrix. The order of the global mass matrix is 6 cross 6. We have a constant rho A L by 420 and the variables are V1 theta 1, V2 theta 2, V3 theta 2. Here we have V1 theta 1, V2 theta 2 and V3 theta 3. Coming for element 1, we have the order as V1 theta 1, V2 theta 2 cross V1 theta 1, V2 theta 2. So filling up the values, the global mass matrix will be 156, 22L, 54, minus 13L, 22L, 4L square, 13L, minus 3L square, and 54, 13L, 156, minus 22L, minus 13L, minus 3L square, minus 22L and 4L square. Coming for element 2, let us pick 4 elements at a time. So if I pick these 4 elements, the order will be V2 theta 2 cross V2 theta 2. So if I pick and place V2 theta 2 cross V2 theta 2, it is overlap. So adding 156 plus 156, I will get 312, 312, adding 22 minus 22, it is 0. Here also it is 0. Coming for 4L square, I will get 8L square. Now coming for these 4, V3 theta 3 cross V2 theta 2. So V3 theta 3 cross V2 theta 2 will get 54 minus 13L, 13L minus 3L square. Now coming for last 2 rows, it starts at V2 and ends at theta 3. So starting at V2, ending at theta 3, if I fill, I will get values as 54, 13L, 156, minus 22, L. And the last row is minus 13L, minus 3L square, minus 22L and 4L square. Fill the unfilled positions with zeros. This completes the global mass matrix for the given problem for case A using consistent mass matrix. Now moving for step 6, to find the natural frequency or eigenvalue, we know that the step 6 to find eigenvalue using which I can find the natural frequency for the given problem. To find the eigenvalue, we already know that we should use the condition to make the characteristic equation to be non-trivial. The condition to obtain the non-trivial solution for the problems on dynamic analysis can be used to find the eigenvalue. That condition is nothing but the determinant of global stiffness matrix minus eigenvalue times the global mass matrix must be equal to 0. Now we already know the global stiffness matrix and global mass matrix is already known to us. So if I fill the matrix and solve, I will get the global stiffness matrix which we have already calculated in our step number 3. So using which I will get, we have EI by L cube common. The global stiffness matrix is given by 12, 6L minus 12, 6L. 6L minus 12, 6L. And we have 4L square minus 6L, 2L square plus 12. So 12 plus 12 is 24, 0, 0, 8L square. So here we get minus 6L and 2L square. So completing the global stiffness matrix, I will end up with 6L minus 6L, 2L square minus 12, 6L minus 6L, 2L square +12 4L square minus 6L and minus 6L. So I have entered the global stiffness matrix using step number 3. So referring to step number 3, I have entered the global stiffness matrix, and now we have minus lambda times the global mass matrix. The global mass matrix is here itself. We have rho A L by 420 common, that is lambda rho A L by 420 times 156 22L 54 minus 13L 0 22L 4L square 13L minus 3L square 0 54 13L 312 0 54 minus 13L minus 13L minus 3L square 0 8L square 13L minus 3L square 0 54 13L 156 minus 22L minus 13L minus 3L square minus 22L and 4L square. This determinant must be equal to 0. So this is the condition to obtain the eigenvalue or to make the solution non-trivial. Now, if I apply the boundary condition for this equation, we have the boundary condition as node number 1 and node number 3 are completely fixed. So therefore, V1 theta 1, V3 theta 3 are all equal to 0. So that is applying the boundary condition for step 6. Applying the boundary conditions, that is V1 is equal to theta 1, which is equal to V3, which is equal to theta 3 are all equal to 0. Therefore, eliminate the corresponding row and columns with respect to V1 theta 1, V3 theta 3. If I do that, eliminating row corresponding to V1, that is first row, and theta 1, that is second row. Coming for V3, that is fifth row and sixth row. Similarly, I should eliminate row and column with respect to V1 theta 1, V3 theta 3 in both global stiffness matrix and global mass matrix. If I do that, eliminating first column, second column, fifth column and sixth column. In mass matrix also first column, second column, fifth column and sixth column. The matrix which is remaining to be solved is EI by LQ, determinant of EI by LQ into matrix of 24 0 0 8 L square minus lambda rho AL by 420 312 0 0 8 L square, which must be equal to 0. So this is the matrix which should be solved after applying the boundary condition. To solve this condition, let us divide the equation by EI by L cube. If I do that, throughout divide by EI by L cube, I will get the expression as determinant of 24,008 L square minus L cube into L into the L power 4, that is lambda rho A L to the power of 4 divided by 420 EI into 312,008 L square. This determinant must be equal to 0. Now let this value can be taken as beta. Let lambda rho A L to the power of 4 divided by 420 EI be considered as beta. Substituting and simplifying, I will get the equation as determinant of matrix of 24,008 L square minus beta times 312,008 L square must be equal to 0. So now solving this further, I will get determinant of 24 minus 312 beta 0. Again we have 0 and finally we have 8 L square minus 8 L square beta. This must be equal to 0. Now if I find the determinant, I will get the equation as 192 L square minus 2496 L square beta minus 192 L square beta plus 2496 L square beta square is equal to 0. Now taking L square common and setting it to RHS and rearranging the terms, I will get the standard equation as 2496 beta square minus 2688 beta plus 192 must be equal to 0. So solving this equation using calculator, I will get the value of beta 1 as 1 by 13 and the value of beta 2 as 1. As I said, one should write the eigenvalues in increasing order. So therefore, beta 1 is 1 by 13 and beta 2 is 1. So this will become the reference for determination of fundamental natural frequency. Now we already know that beta is given by this expression. Substituting for beta, I can find lambda. So if I do that, I will get, using this equation, lambda 1 rho A L to the power of 4 divided by 420 EI is equal to beta 1. So beta 1 is 1 by 13. So now simplifying which, I will get the value of lambda 1 as lambda 1 is equal to 420 EI divided by 13 rho A L to the power of 4. And we already know that the eigen value is nothing but the square of the natural frequency. So therefore, the fundamental natural frequency omega n1 square is equal to lambda 1 So therefore omega n1 is equal to square root of 420 EI divided by 13 rho A L to the power of 4. So if I simplify, I will get the fundamental natural frequency for the given problem using consistent mass matrix for analysis as 5.68 by L square root of EI by rho A. So this is the solution for case A, in which we have calculated the fundamental natural frequency of transverse vibration of the fixed beam given in the problem using consistent mass matrix for analysis. Let us move on for case B, that is determination of fundamental natural frequency using lumped mass matrix for analysis. Now coming for case B, step number 1 to step number 3 remains same, that is till obtaining the global stiffness matrix. Coming for step number 4, that is element mass matrix. Now I should use lumped mass matrix for analysis. We know that the lumped mass matrix for beam element is given by rho A L by 2. Keep half at one node, another half at another node. 0 0 0 0 0 0 0 0 0 1 0 and 0 0 0 0. Substituting the values of rho A L of element 1 and element 2, I can get the lumped mass matrix of element 1 and element 2. Now the values of rho A L for element 1 and element 2 remain same, which are nothing but rho A L, the mass density, cross section area and length. So therefore this itself is the element mass matrix for element 1 as well as for element 2. If I write it, I will get the element mass matrix as for element 1, mass matrix of element 1 is equal to rho A L by 2 1 0 0 0 0 0 0 0 0 0 1 0 0 0 0 and 0. The nodal variables are V1 theta 1 V2 theta 2, V1 theta 1 V2 theta 2. So similarly for element 2, if I write, I will get the element mass matrix of element 2 as rho A L by 2 1 0 0 0 0 0 0 0 0 0 1 0 and 4 zeros. The nodal variables are V2 theta 2 V3 theta 3, V2 theta 2 and V3 theta 3. Now we already know the order of the global mass matrix is 2n cross 2n, where n is number of nodes. So therefore the order of the global mass matrix will be 6 cross 6. Using the same procedure which we have used in case A, I can write the global mass matrix for case B as step 5, global mass matrix M is equal to rho A L by 2 common, I will get 1 0 0 0 0 0, adding 1 plus 1 is 2 0 0 0 double zeros, again we have 0 0 1 0 0 0 0 0. Now fill the unfilled position with zeros. You get 0 0 0 0 Here also I get 0 0 and 0 0. Moving on for step 6. Step 6 is to find eigen value. So this I have noted out from step number 3, which is common for both case A and case B. Now minus lambda times the global mass matrix for lumped mass system analysis is known to us. We have rho A n by 2 as common, multiplied by 1 0 0 0 0. This determinant must be equal to 0. Now applying the boundary condition and solving, I will get now the boundary condition for the problem is node number 1 is fixed and node number 3 is completely fixed. Therefore V1 theta 1, V3 theta 3 are all equal to 0. So eliminating the rows and column corresponding to these 4 nodal variables, eliminating first row, second row corresponding to V1 theta 1, fifth row and sixth row corresponding to V3 theta 3. So similarly eliminating the column 1 and 2, 5 and 6, and also in mass matrix column 1 and 2, 5 and 6. The remaining matrix which I should solve will be determinant of PI by L cube into 24 0 0 8 L square minus lambda rho A L. If I multiply 1 by 2 inside, 2 2 will get cancelled. I left out with 1 0 0 0. This determinant must be equal to 0. Now let us divide throughout by EI by L cube. If I do that, throughout divide by EI by L cube, I will get the determinant of 24 0 0 8 L square minus lambda rho A L to the power of 4 divided by EI times 1 0 0 0. This determinant must be equal to 0. Now let us take this value as beta. Let lambda rho A L to the power of 4 by EI, let us take it as beta. So substituting which I will get determinant of 24 0 0 8 L square minus beta times 1 0 0 0 must be equal to 0. So further simplifying this determinant, I will get the determinant of 24 minus beta 0 0 8 L square must be equal to 0. So if I find the determinant, I will get the value as 192 L square minus 8 L square beta is equal to 0. So if I further simplify, I will get the value of beta as beta is equal to 192 divided by 8. Now I can find the eigenvalue and natural frequency. That is, substituting the value of beta, we have beta is given by lambda rho A L power 4 by EI. That is lambda rho A L to the power of 4 by EI is equal to 192 by 8. If I simplify, I will get the value of lambda as 192 by 8 will gives us 24 EI by rho A L to the power of 4. So this is the eigenvalue. We know that eigenvalue is nothing but square of the natural frequency. So therefore, the natural frequency for this problem using lumped mass analysis, we have omega n square is equal to lambda. So therefore, omega n is equal to square root of 24 ei by rho a into the power of 4, which gives us the natural frequency as 4.9 by L square into square root of ei by rho a. So this is the solution for case B, in which we have calculated the fundamental natural frequency for the fixed beam by using lumped mass analysis as 4.9 by L square root of ei by rho e. Let us move on for case C and find the percentage error for case A and case B. Now coming for the final case, to find the percentage error, first let us calculate the percentage error by using the consistent mass matrix for analysis. The percentage error is given by the general expression modulus of difference in exact value and the calculated value divided by the exact value multiplied by 100. Now, the percentage error by using consistent mass matrix for analysis is equal to, the exact value is 5.59 by L square root of ei by rho a minus the calculated value is 5.68 by L square root of ei by rho a whole divided by the exact value is 5.59 by L square under the root ei by rho a. This modulus multiplied by 100. When I solved, I got the error for determination of fundamental natural frequency using consistent mass matrix as just 1.6%, whereas the percentage error obtained when I used lumped mass matrix for analysis, modulus of the exact value is 5.59 by L square root of ei by rho a minus the answer by lumped mass matrix analysis is 4.9 by L square root of ei by rho a whole divided by the exact value is 5.59 by L square into root of ei by rho a. There is a huge difference in error between consistent mass matrix and for lumped mass matrix. With this analysis, it is clear that always one should prefer using consistent mass matrix for dynamic analysis of structures. So this is the complete solution for the given problem. We have calculated the fundamental natural frequency of fixed bar using consistent mass matrix, using lumped mass matrix, and also we have compared the results. Thereby we have completed our discussion on dynamic analysis. From next lecture we will be heading to discuss the axis symmetry problems in finite element analysis. That's all from this lecture. Thank you.